Good evening. I'm Samuel Sivi, coordinator of the Young Actuaries Initiative, and I'm happy to welcome you to this new webinar. Tonight, we have the great pleasure to have Wilma Guevara Alkonen, winner of the 2024 SCORE Actuarial Prize in Sweden, will present us our work on claims reserving with machine learning techniques. As usual, you can ask your questions via the chat, and Wilma will answer them at the end of the presentation. Wilma, the floor is yours.
Thank you. And thank you for having me. So my name is Vilma Guevara Härkönen, and I work as an actuary at Folksam. And today I will present my thesis on claims reserving with machine learning techniques. So the agenda for this evening will be the following. I will first start by going through a brief introduction to reserving and to the problem. Then I will explain the methods that have been used in this work. After that, we will look at the results, and finally, I will share my conclusions. So as you know, reserving is about the fact that an insurance company needs to set aside money to pay compensation to customers who suffer for losses. And we actuaries calculate and ensure that the reserve corresponds to the expected future claim cost. To estimate the size of this reserve, well-established traditional statistical models are used, which have been the industry standard for decades. Machine learning methods, on the other hand, are still relatively new in this context and have not yet been widespread in the industry for reserving. However, interest in them has increased significantly in recent times. So the purpose of this thesis was to implement 3 different machine learning models to estimate reserves and cash flows, and to compare these then with traditional models to see whether machine learning could be of interest for reserving. So in other words, can we obtain at least equally good estimates of reserves, or hopefully even better ones with machine learning? And what I found is that machine learning actually gives closer estimates to the reserve size in those test cases that I've been looking at. And moreover, I could also see that in cases where the traditional models systematically underestimated the reserve, the machine learning was able to correct this. But we will come back to this later on when I show the results. So just briefly about the reserving models. So the information we currently have and using the traditional reserving models, as you know, includes the number of claims to date, the claim cost to date, the date the loss occurred, the date the claim was reported to the insurance company, and the dates of payments made. And what we aim to achieve is to predict the future and estimate upcoming payments for claims that have already been reported. But in addition to that, we also have to consider claims that have already occurred but have not yet been reported to the insurance company. So it's our job to estimate how many of those unreported claims we will receive and their associated costs as well. And as you know how we do this, we use historical data and apply statistical models to estimate the expected number of claims and claim cost. Traditionally, in non-life, we use chain ladder model. And also another model to consider is an over-dispersed Poisson model that is an extension of chain ladder model, but in the ODP model. So we take the chain ladder model and then we have the development period that we will divide into two. So what is the traditional development period will then be divided into a delay in reporting to the insurance company, and then time from reporting to the payment that will be made. So then the triangular that we usually have in non-life will be three-dimensional, but both uses the same assumptions of Poisson modeling. So these two models, chain ladder and ODP model, will be benchmark to which the machine learning models are then compared to. So then we move on to the machine learning models and starting with gradient boosting machines, GBM. These are tree-based models where observations are split using simple yes-no questions. These models can be illustrated like a tree-like graph, as we can see here, and hence the name tree-based models. So to explain the model structure a bit, so the model has 4 different hyperparameters that will be fitted to the data. The first one is depth, and that is how many times we divide the feature space. So how many times we will divide and ask these questions. Then we also have bagging, that is how big proportion of the training data will be used to build each of these trees. We also have shrinkage, that is how big portion each tree will be for the bigger estimate. But now I realize it's easier if I explain one tree model first before explaining the GBM model. So one tree is here, as we can see illustrated in here. And in this case, the feature space is divided by asking these questions. So if we start by up here, so here we see that the expected claim cost is 33,000 and 100% of the observations are in this leaf. Then we ask a question. Has the claim been reported to the insurance company within 1 year from the claim date? If yes, then the observation will end up here. And here the expected claim cost is 2,000 and 79% of the observations will end up here. But instead, if the claim was reported to the insurance company within a year from the claim date, then the claim will end up in here. And the expected claim cost is 148,000. And here we have 21% of the observations. And from here, we divide them further on. And here we look at, okay, how long time did it take from that the claim was reported to the company to after the claim was paid out to the customer. If it was within 1 year, the claim will end up in here and the expected claim cost will be 559,000. And otherwise it will end up in here. And then we ask another question. So in this way, we can divide the feature space and you can build as big trees as you like. You can ask as many questions as you like. But the problem is that as we can divide the observations in this way and build big and complex trees, then there's quite big risk for overfitting the model to the data. And that is where the gradient boosting machines come in. So the idea of gradient boosting machines is to combine these weak estimators. So combine, because we can say that one tree is a weak estimator. So with gradient boosting machines, we combine multiple weak estimators for a stronger estimator. So the estimate will be a sum of these trees. And then we come into the hyperparameters. So as I said, depth is how many times we divide the data into these questions. Bagging is how big proportion of the training data we will have in each of the trees. And this bagging can be good to reduce variance, and it helps prevent overfitting. Shrinkage is then how much each tree will contribute to the final result. So lower the shrinkage factor, the more trees are needed for a good model. Then a minimum number of observations per leaf, that is also one estimator, and that is how many observations we want to have at minimum on each of these leaves here. So higher value here makes the tree less complex, and in that way it will also reduce the risk of overfitting. And the tree models, they are quite popular because they're easy to interpret and visualize. However, the downside is that they can be easily be overfitted to the data. Then, so GBN was one of the models. Then I have built two models with neural networks. So now we can move on to the neural network part. So neural networks, they are algorithms that are loosely inspired by how the human brain works. And here we can see the mathematical construction of the algorithm. So the neural networks, they are as functions that are changed to each other. So in this case, we have the function for one layer H. And as we can see, the input to that layer is the layer H minus 1. So that's the previous layer. Then that will be applied to a weight matrix and a bias vector. And then we also have an activation function that will be applied element-wise. So activation function could be linear or exponential or something else. So then to illustrate this in a neural network architecture of one of the models that I had. So we have the figure in here. And this is the more simple model. In this neural network model, I have modeled the claim counts and claim amounts in their separate neural networks. So if we start by looking at this model, this we assume that this is the model for the claim counts. So the first layer here, this is where the input comes in, and this is called embedding layer. And the inputs in this neural network model is coefficients from the traditional ODP model. And in that case, it will be the inputs for accident year and reporting delay. When we are modeling the claim amounts, then we will have three inputs in this model. We have one for accident year, one for reporting delay, and one for payment delay. So we start by putting the inputs in the neural network model. Then they come into embedding layer, that is just to take hand of categorical variables in the neural network model structure. But from this start point, then the inputs will come into the first hidden layer. So the dots here, they illustrate the number of neurons in each layer. In this case, the first layer had 20 neurons, the second 15, and the last 10. And if you would then draw lines here between all of the neurons, so then you could see that these build the network. But the observations, they come here to the first layer and then they move forward to the last layer. And we call these for hidden layers because we will never get to see what is the output from each of these layers. Yes, and finally, after the hidden layers, they will come here to the output layer, and this is where we get the result from the neural network. That will be the predicted number of claims. The green line here, that is called skip connection. This is where we connect the inputs, in this case, the predictions from the traditional ODP model to this neural network. And we do this connection, so this will slightly speed up the neural network process. And since the estimates from the traditional reserving model are inputs here in the neural network model, then all of this can be thought of as a neural network boosting of a traditional reserving model. So here is then the architecture of what I've called a double neural network model. And in this case, the claim numbers and the claim amounts are modeled in the same neural network model. So that way, the idea here is that perhaps the claim numbers and the claim amounts have some nonlinear dependencies that the regular models or the neural network model, where we model the claim numbers and claim amounts separately in their own models and then multiply with each other. So those models cannot really catch those kind of nonlinear dependencies that we might have in the data. So here comes in this double neural network model. And this is quite similar. The first part here, the blue boxes, are quite similar as we saw in the previous picture. We have the inputs here as well from the traditional reserving model that will then be put into the embedding layer. Then here, the green boxes, these illustrate the ones where the claim counts are modeled. And in here also, it is important we have something what we call ordered claim counts layer. It is also important in this model that we keep order of the claim counts so that we will apply only the claim counts that we have seen in the data to the predicted claim amounts for those kind of claims. And then we will also have the number of claims that will be predicted of the model that have not been reported yet. And then it's important to separate these so we keep track of what we have already seen in data and multiply those with the predicted claim cost that belongs to those kind of claims and those that we predict. But here the green boxes are for the claim counts, and then the purple boxes here, these illustrate the parts that is for the claim amounts. So here we have the element-wise product of claim counts and claim amounts that will then build the total claim cost. So the output from this double neural network will be two vectors, one that is for the claim counts and one that is for the claim amounts. And these as well are connected to the traditional reserving model ODP. So this as well can be thought of as a neural network boosting of the traditional model, but slightly more difficult and complex than we have when we model the claim counts and claim amounts separately. So this box here illustrates the green line that we saw in the previous picture. So moving on to looking at the results of these models. So the data that I've used in my thesis is partly simulated data and partly real-world data from Folksam. So the simulated data set is based on real Swiss insurance data, and here's the reference to the claims simulation machine. So from this claims simulation machine, completely new fictional data sets are generated depending on the desired characteristics in the data. The simulated data set that I used included 6 different types of insurance products or lines of business, and each of these had 12 accident years, and all the claims were fully paid out within 12 years. The claims occurred between 94 and 2005. And the data from Folksam instead. Folksam is one of the 4 big insurance companies in Sweden. And from there, I have looked at 3 different products or lines of business where the time until claims were fully paid out varied between 10 to 16 years. These claims occurred between 90 and 2007. So the main difference between these 2 data sets is that the simulated data, of course, was easier to handle and predict compared to the real data, where events such as policy changes can affect patterns, payment patterns, making them much more difficult to predict. But it is also, of course, interesting to see if these models can handle real-world data because that is where it's interesting to use in the industry. So a few words about training of the models. As I mentioned, there is some hyperparameters in the models that have to be trained before so that we get as good a model as possible. Here are some examples from training of the GBM models. So there we had 4 different hyperparameters, depth, bagging, minimum number of observations, and shrinkage that we can tune so that we get as good possible model for each of these lines of business. And in this case, there was no huge difference between the model fits within the standard fit from the GBM package or that we choose. But the same goes also for the neural network models. With neural networks, there is plenty of hyperparameters that can be tuned. There is the number of hidden layers, the number of neurons, and so on. So after we have tuned the model and find the best possible fit of the hyperparameters to the data, then we apply the model to predict the reserves. And here we can see the result with the simulated data. Here we have the true reserve. Then we have the chain ladder predictions. We have ODP predictions and then GBM and neural networks, the more simple one and the double neural network. And as we can see here, for all of the lines of businesses, there is some machine learning model that is better than the traditional model. And in most cases, all of the machine learning models are somewhat better. The absolutely best results was here for line of business 1, where the GBM differed only 0.02% from the true reserve. So that was very close. And what we can also notice here that the GBM model in most cases was the best to predict the total reserve. So here in 4 of 6 cases, the GBM model was the best. In one, the simple neural network, and in one case, the double neural network. If we then look at the results with the real world data, the first thing that we can notice that there is quite a big difference if in the bias with the traditional models here as of most here for the line of business 1, the traditional model underestimates with 45%. With ODP, the underestimation is somewhat better, but still at 37%. With GBM instead, the bias was 7%. But as we can see here, the GBM did not underestimate the reserve, as we can see for all the other models. Then even for the other line of businesses, the predictions were better with the machine learning models. Here for line of business 2, the prediction with simple neural network model was minus 0.15%. And with the third product, the GBM had a bias of minus 19%. So that was not as big difference as we saw with the other models, but still better than with the traditional models. So after feeding the models, as I said, I was able to conclude that in all cases, both simulated and real data, one of the machine learning models produced a clear closer estimate of the reserve than the traditional models. Among the machine learning models, GBM gave the closest result in 6 of 9 cases in total. And as I said, the best estimate being only 0.02% off from the actual outcome. So here we can then see an illustration of the results for that particular product. And the vertical axis represents the accident year, and the horizontal axis shows the time is the development year. And here we see the bias illustrated in as a heat map. So the blue cells indicate where the models underestimated the actual payments, and the red cells illustrate where it overestimated the actual payment. So as we can see here, the traditional model in the top left and the neural network models, the reserve is systematically underestimated. But then, however, for GBM, there is more red cells. So these red cells instead then helps to balance the underestimations, and this will then result in a better prediction overall. And you can also notice here that there is quite red cells here at the end of here in the corner. But even though the relative bias here is quite high, it doesn't really have a material effect because the payments here in these four cells are quite low. So this is only the relative bias that will be quite high here. So then we can take a closer look at how well the traditional and machine learning models performed um, by examining the cash flow and the average claim amount. So we start here at the top, where we have an illustration for an insurance product from the simulated dataset. And here below we have for a real-world dataset. If we look at the cash flow for the simulated dataset, we see that all of the models, the traditional and the machine learning models, captured the cash flow very well, and they followed the pattern nicely. The average claim amount over time was a bit more trickier to catch. So it varied quite over the years, but all of the models could model it quite nicely. But here we can instead see that the GBN model had more difficulties with modeling um, the, the right pattern in the average claim cost. Instead, it didn't really catch the downfalls here. Instead, it's more like flatten trend in the claim cost. So it gives the GBM model then provides us a more rough estimate on the claim cost. So, but then if we look at the performance on the real data instead, here we can see much greater differences. Here we can see that the GBM did not really capture the payment structure properly. At first, it overestimates the payment. And then when it peaks, when the payments peaks here after one development year, the GBM model doesn't really catch that either. And then in the tail, it overestimates the payments. And when it comes to the average claim amount, here for the first accident years, all of the models quite nicely capture the average claim amount. But further on, it becomes difficult for all of the models. Here, the pink line is the true claim cost. And as you can see, all the models capture it quite nicely here in the beginning, but somewhere after 12 years, it becomes very difficult. And here, all of the models underestimates. But before underestimating, GBM instead overestimates over here. And this is for the product that we saw the biggest difference between the traditional models and the GBM model, where the traditional were approximately 45% off, and GBM instead were 6-7% off from the true cost. So what we can see here that that the reason why GBM gives a better reserve in total is because of it gives a more rough estimates. So it doesn't really capture the true pattern in the cash flow or in the average claim cost. It can also be said that the reason why all of the models here for the latest accident years fail to model the average claim cost, that is because of the payment structure was very different in here. And the first payment periods have very low payments, and then they came a lot of payments in the end. So that is the reason why it was difficult for all of the models. So what about the variation in the models? Previously, I have only fed the models for only one data set, but it is also interesting to estimate how much variation these models actually have. And in order to do that, I have calculated the root mean squared error of prediction. And this is conditional RMSAP that is semi-analytical. So the variation part here is analytically calculated. And the estimation error is with parametric bootstrap with 1000 simulations for all the other models except for neural networks, where I have taken 100 simulations instead because of the computation time was so much more longer for the neural network models. So we find the lowest MSCP for chain ladder and ODP. And that is also expected since the machine learning models have many more parameters. And therefore we can expect higher estimation errors. The GBM has higher estimation errors than the neural network. And the lowest variances we find for neural networks and chain ladder. But here we can note that the estimated values from the models here are assumed to be true ones. So this does not really capture the model error. Therefore, it would be interesting instead to compare the unconditional MSCP instead. And this could be done, for example, by simulating 100 times from the simulation machine, and after that refeeding the models for each time. Because in this case, if the model is completely wrong, then we can still get low values on the MSCP. So to conclude, my conclusion is that machine learning has potential for improving reserving. But then arises the question, which model is the best? And here there are different aspects that can be taken in consideration when trying to deciding which model is the best. So if we want a model that provides the best estimate of the total reserve, then GBM would be the best option. if we want to have a model that has least variation, then chain ladder or neural network would be go-to. Also, if we want to minimize the estimation error, then traditional models, chain ladder or ODP would be the chosen models. But then on the other hand, if you would like to have a machine learning model that has easy implementation, then GBM would be my go-to model because the implementation in GBM is quite easy. You can, in my thesis, we have put the model structure that is very close to the GLM model. So in that case, more programming-wise, you would only need to change, for example, in R, GLM to GBM, and still you can write the model formula as in the GLM model. So GBM is it is more easier to implement than the neural network models. And a few words about improvements. There could be different divisions of training and validation data. In this thesis, I have taken the individual claims and divided them approximately 50-50 to training and validation. That is because of the traditional models, ODP model, the covariates might be depending on the volume of the data. But here you could try dividing the observations differently as well. Also, GBM model handles categorical variables. In this case, I have used the accident year and development period as numerical, but you could also try to have a categorical and see if there is any difference in the models. And also there is a lot of fine-tuning of the neural networks. As I said, there can be tuning of many different hyperparameters. For example, number of hidden layers, number of neurons, activation functions, and so on. So there is a lot interesting things that could be done with the models to improve them even more. There was one question that was about when I talk about the true reserves for non-simulated data, does that mean that you know the final value of all the claims and therefore they are all closed? In other words, can you please define true reserves for non-simulated data? Yes, and in this case, I know the true reserves for those claims, as the accident years were quite early. They were from the 90s to 2007. So at this point, I can already say that all of those products or the claims are already full developed. And that is also a thing with these models. I didn't really mention that, but if you would use this with real world data, then if you would think about the triangles that we have for the chain ladder model, for the training of the models, you would need to hop or jump one triangle above so that you have something that is already fully developed, so that in that case you can compare the predicted reserves from the models to the true ones that are already fully developed. I also have one question that is if the models that I have been developed have been used in my company after the thesis. And yes, we are in the developing process right now to trying to implement this to real world data. And we have had them as an analysis tool to compare the traditional models. So they have not yet been implemented in case that we would actually book and reserve those reserves. And I can also mention that when I showed the real world data and what the traditional models had the reserves for the real world data, those are not the reserves that has actually been reserved by the company. Those are only the ones that are uh, just modeled academically. So those are not the real booked reserves. There's also one question about that the GBN shows high estimation error compared to ODB and chain ladder. And is this due to the model complexity or overfitting, and how it could be improved? And yes, that is, I assume that is because of the higher model complexity, and it is easier to overfit to data. What I've also seen that GBM is more sensitive to the data than, for example, neural network models, and it is also more sensitive to if you would have outliers in the data. Um, and to be proving, you could try to, for example, exclude some of the cells that you have in the triangular to have a bit more robust data so that it doesn't take so much account to each of the cells that you have in the data. And also one question about how do you explain that a machine learning model based on aggregate triangle can work well? Normally you need a lot of data, don't you think? Yes, you need quite a lot of data usually, and but still in this case, for one product that has approximately 12 development years, there is some hundreds of observations that are included in the model, and it still works. But the important thing here, what I've found, is that it is important that in the aggregated data, you have quite a lot of data in all of the aggregated cells. So in cases that there might be many cells more in the tail that doesn't have any payments or doesn't have any claims, then the models becomes, especially GBM model, becomes more uncertain and might overestimate the payments in there. And we might have time for one more question. That is, how many variables did you use in the machine learning models? And the feature variables that I have used in these are only accident year and development period. And so the accident year reporting to the insurance company and the delay in the payment after the reporting to the insurance company. So 3 variables. And also the number of claims are also one variable that comes as an offset to the claim cost models. So thank you. It was a pleasure to be here and present my work. I hope you found it interesting. And yes, thank you very much. Have a good evening.